Good evening, and welcome to tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to take a look at distribution and simulation, key ideas in statistical reasoning. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. I'm really excited to introduce our two panelists tonight, Gail Burrell and Landy Godbold. Gail was a secondary teacher and department chair in suburban Milwaukee, Wisconsin for over 28 years. She is currently a mathematics specialist in the program for mathematics education at Michigan State University. She served as president of NCTM and as the director of the Mathematical Sciences Education Board. She co-directs the Institute for Advanced Studies International Seminar and the Secondary School Teachers Program component of the Park City Mathematics Institute. She received a Presidential Award for Excellence in Teaching Mathematics and the NCTM Lifetime Achievement Award and is a Fellow of the American Statistics Association. Gail was chair of the Commission on the Framework for Advanced Placement Calculus and serves on the College Board's Academic Advisory Committee and Advanced Placement Calculus Development Committee. Gail is currently a Senior Mathematics Advisor for Texas Instruments Education Technology and is a T-Cube National Instructor. Her research interests are statistics education, the use of technology in teaching secondary mathematics, and issues related to what it means to teach mathematics. Gail, thanks so much for being with us.
Thanks, Mike. I'm really happy to be here.
And Landy holds both his bachelor's and master's degrees in applied mathematics from Georgia Tech and retired after 40 years of teaching mathematics at the Westminster School in Atlanta, Georgia. He introduced statistics as an elective course early in his tenure there and was actively promoted the teaching of statistics since his participation in the Woodrow Wilson Summer Mathematics Institute, where he focused on statistics in 1984. A recipient of the Presidential and Tandy Awards for teaching, he is a T-Cube National Instructor as well and a member of the authoring team for the Statistics-inspired instructional site. He continues to look for new ways to use technology to help students understand subtle statistical concepts. Thanks so much for being with us, Landy.
Glad to be here.
We're expecting a large crowd, so your audio is muted. Feel free at any time to send any questions to Landy or Gail using the Q&A window on the right side of the screen. This session is being recorded, and as a reminder, we'll provide a link to the event certificate of attendance at the conclusion of the webinar. Once that recording is available, we'd love for you to follow along at that point with your handheld or your software. It makes it a lot easier. That way you can go at your own pace. You can pause and rewind the recording as necessary. We hope you don't have any audio issues tonight, but in the event that you do, try selecting Communicate from the WebEx menu and choose Audio Broadcast. At this point, Gail is going to discuss our agenda.
Thanks, Mike. So welcome, everybody. Tonight, as Mike said, we're going to talk about distributions and simulation. They're probably common ideas, but we hope we're going to give you some new ways to think about how we can help kids understand these. We're going to start with some introduction to data, looking at the distribution and summary statistics. Then we're going to turn it over to thinking about inference, and we'll close with talking about some online resources. And hopefully you guys will all stick around for the webinar giveaway at the end. So hang in there for that.
Thanks so much, Gail. And Landy is going to discuss our expected outcomes.
Really we're looking tonight to look at really from a start to finish kind of thing, how do I want to say this? The through line, I guess, of looking at data from the very beginning, collecting the data, and then making inferences about it. We're going to use TI technology do that. And we're going to be focusing primarily on the understanding of the ideas behind statistical inference and statistical data analysis. Keyword being variability, and distributions are ways that we're allowed to see how those distributions and that variability plays out.
Thanks so much, Landy. Gail, it's all yours.
Okay, thanks. Let me get my desktop shared here. And I want to actually start from this one. Okay, I want to start right here. Suppose you're given the maximum speeds for a variety of animal types. Predict what you guys think the typical speeds will be. So, for example, what do you think the typical top speeds of land animals would be? So why don't you fill it out in the chat window? Just offer up some things, and Landy will pay attention and call out what some of you are estimating for these typical top speeds. So we got some answers, Landy?
Got a few, got in the 30s and in the 60s right now. We have a 2 and a 22.
Oh, all right, awesome. Well, let's look at the data. Okay, wrong way. All right, so here's the data in a list. And as you can tell, we can scroll through the numbers, but it's not very easy to actually get a sense. I don't see a 2 though. I don't see anything as big as a 60. So the kind of looking at a list doesn't help us really get a grasp of what's typical. So I'm going to go back to this graph, this distribution of the maximum recorded speed of land animals. And once you look at this, you might, first of all, you might wonder, what does anybody wonder about? Are there some questions you might want to ask? Again, you can type it in the chat. But when you look at a distribution of data, you kind of like want to think about some of this. Someone asked me if you've seen both is recorded in there. Well, I don't know. Let me just check that out and see if I look up Bolt. I don't know if I can find him or not. Let's see. I'm not sure he's in there. But we can actually go through and check that all out. Do we include sales and sloths? All right. So this is a subset of all these animals. But so what you guys are wondering about are particular instances of one idea, one thing. In stats, we really want to talk about what is typical. What do we see that might be unusual, and what do we see overall over the whole pattern that would be typical of this land speed? So I'm looking to see questions like, what's going on in here? This is a good question. Is 70 an outlier? And who does 70 belong to, by the way? It's a cheetah. So that seems to be the fastest land animal of these speed of these types of animals that we have. So we care about this kind of the shape of the distribution because it can help us think about what the center is, what's typical. This distribution, the kids in the 6th grade use language like mound shape and relatively symmetric to describe a distribution like this. If I were to go and look at, say, all animals, I'm going to get a different shape of distribution. And this one is slightly skewed. For 6th grade, I don't really care if it says it's skewed right in the direction of the tail. Some of you might be wondering who this guy is. Does anybody know? Who's this guy sitting out there? You're right. Joe Peters is right. It's the peregrine falcon. We can actually check out what some of these are, and it kind of looks like we can see, there's a lot of these ones up here are birds. We can look down here and see, oh, the porcupine isn't so fast. But again, the idea here is we can get a sense of where the typical speed is. No, it's not the Atlanta falcons.
Sure it is.
That's the peregrine falcon right there. All right. Okay, so we're really looking at ways to describe what's going on. We could explore other kinds of distributions, but I want to move now to thinking about the mean. So the mean is something that you guys, the kids all know, but I really do think, this happens to me when I'm teaching and I ask my kids what the mean is. They answer, it's what you get when you add everything up and divide. And it's not clear to me that they really have a conceptual understanding of what the mean is. So this is an activity from Building Concepts, which is another one of the TI resources online. And I've got 4 dogs, and I'm going to say go, and these dogs got a bunch of dog food, okay? But I want to have fair share. Every dog should have the same amount of dog food. And so one of the ways that I can do that is to take from the guy that has the most, the dog with the most dog food, and give some of his dog food to the one that has the least. Well, it looks like I'm a little bit short here, so I'm going to have to figure out some way to split those bags of dog food into 4, and I can, or maybe a half, or maybe you guys could figure out a better way to split them. So I have to split this guy into 4ths. And while I'm doing that, you guys are probably thinking, oh, there's a better way to do that. So if I get this guy, now what do I have to do? So if I split this guy into 4ths, right, and I move that up there, oh, I can see that every dog has, what is it, 1, 2, I can count, and 3/4 of a bag. So fair share, and one way to think about that, the mean is saying, if I were to take from the most and give to the least, everybody in the end would have the same amount. But I want to look at another one, another way to think about this. Here's my same 4 dogs. I'm going to give a bunch of dog food. I'll just let's use 18 here. Okay? So I have 18 bags. And this time, I'm not going to take from the most and give to the least. Instead, I'm going to pool all of the dog food. And then I'm going to allocate it by dividing it among those dogs. Now, this is a very different way of thinking about the mean from the fair share, where you were taking from the most and giving to the least. And one of the things that I feel is important is that kids understand both of these ways of thinking about the mean. Which of these ways is more closely related to the standard add them up and divide? The pooling way, or the one where I take from the most and give to the least? And I kind of think it's this pooling way that's more closely related, so I agree with what some of you are saying. But it's important that the kids have that taking from the most and balancing, giving it out. That's an important way to think about the mean, and it gives them kind of a conceptual understanding. Now I want to actually go to a different way to think, and this comes from thinking about a tournament like a soccer tournament. And we don't really care about what kind of a tournament, if it's, if it's an elimination or how it works. We just really care that if the teams were evenly matched, they would have scored 6 goals each. And the total number of goals in a tournament was 54. So I want you to think a minute about what a graph or a distribution might look like if exactly 3 of the teams had 3 goals, 1 team had 10, and every team had at least 1 goal. Under the constraint that the total number of goals still has to be 54. So while you're thinking about that, I'll give you just a little minute to mull over what that might look like. How many teams? Well, can you figure that out? Good shot. So they would have to be 9 teams. And basically what I'm thinking about here is, all right, 1 team had 10 goals. 3 teams had 3 goals. And my constraint was that I had to have 54 total goals. So I have to figure out some way to increase the number of goals to get to 54 goals. Oh, I'm getting close. Ooh, I got to 54 goals. So the idea here is that if I'm thinking about the mean has to be 6, and I have 1 team with 10 goals and 3 teams with 3 goals, what I'm trying to do is to find a way so that I can keep the mean at 6. And I can create different distributions. Oh dear. Anybody know what I should do now? Aha. So here's a different distribution where the mean is 6. Okay. So here's the task. I'm going to flip to a PowerPoint here. Suppose I had my kids in my class, which I do this all the time. They have several different tournaments depending upon the constraints. And the question here is, which tournament has the least evenly matched teams? Which tournament has the most evenly matched teams? So the kids are looking at all these different distributions, and they're trying to figure out, okay, in kind of statistical language, in which tournament would there be the greatest variability among the teams? How can I measure the variability? So it takes a little bit of thinking on their part and a little bit of conjecturing. But it's not too long before the kids realize that in order to measure the variability, to get some kind of a sense of how these distributions are spread around the mean, you can count the deviations from the mean of each one of your data points. So this would be a deviation of 2. Here would be 2 deviations of 3, so that would be deviations of 6. Total deviation 7, 8. Add in a 4 here, so the total deviations on this side is 12. It doesn't take too long before the kids figure out that there's got to be 12 deviations on this side, which brings up the notion of mean as a balance point. So not only is mean fair share, it's also the balance point of a distribution. And it's the balance of the deviations of each of the values from the mean. Now, you can think about this, if we were to go back to my PowerPoint, and we look back at this, you can see that then you could associate with each one of these distributions a number that would describe the total of the deviations. And that gives you a way to measure the variability from the mean. And this notion of measuring the variability from the mean is the third part of this trio of seeing the distribution, the shape, the center, and the spread around, or the variability around the mean. So getting kids to have this multiple perspective on what the mean is an important part of building the foundation. The last little piece, this is 6th grade, and it's called the mean absolute deviation. And you have to get to the mean because you may have different values or different numbers in your tournament. When kids then look at distributions, so here are the distributions of points correct for some quiz or something that some classes got. They can estimate where they think the balance point of the distributions will be, and they can estimate or actually even compute what the mean absolute deviation will be to get a sense of what the mean plus or minus this mean absolute deviation is going to look like. And they can play with different sets of this so that they can get a sense that Here I can see that the average deviations, okay, is just a little bit over 1 on either side of the mean of 12. So this sets the stage for kids to develop this understanding of what a spread or variability means around the mean. And I just want to close this little part by thinking about, okay, how do I move from this mean absolute deviation, which is a 6th grade concept, how do I move from there to high school, to the standard deviation? So you can take exactly the same situation. And basically, all you have to do is tell the kids, so we're not going to take the absolute value, and you can give them reasons why. Instead, what we're going to do is square. Squaring will give us a more stable way to think about what's going on here. And because I squared, I have to take the square root. So it's exactly the same idea of finding the deviation from the mean, squaring the answer to avoid adding them up and getting 0, and then dividing by the number of data points, but then square rooting at the end to come back to the unit that you're talking about. I don't even show my college, I teach stats to elementary pre-service teachers, I don't show them this formula. They don't need that formula. They're very comfortable thinking about the mean as this number of deviations, the way to measure variability. And the formula would just like scare them away. So those of you that teach AP stats, you need the formula. But getting kids going, you don't need it. Okay, so I am going to turn this over to Landy. I'm going to stop sharing, and I'm going to move this down to Landy.
You have to drag the little volley thing.
I am. I dragged it to Michael, not to Landy. It's just not, yes. Okay. And Landy's going to pick up and talk about how this foundation then can be used to start moving into inference.
Okay, cool. Thanks, Gail. I like to think of what we're doing tonight as where do we start and where do we go. And for me, the where do we go, at least for the high school curriculum and AP stats, that's formal inference. We're not going there tonight. For AP teachers that are joining us for this program, I hope that what we do here will be a reminder of the fundamental concepts that lead up to and that support that formal inference. Give you an idea of where you might actually be able to help your colleagues in other grades and in your district, because if we take the ideas of the Common Core, what we're looking at is having real statistical thinking taking place in 6th, 7th, 8th grades, not just an AP course. So that's kind of where we're plugging in tonight. For everyone else, if you're not teaching an AP course, tonight is really, I hope, right down your alley. What we'd like to do is have you get a good chance to see and understand the big ideas for the through story, the one that goes all the way to AP. We're going to take a good look at the logic of inference. And I think even high school kids in the AP courses tend to skip past the logic and just say, tell me what to do. You know, what's the procedures? We're not going to be looking at procedures tonight at all, but more the ideas. Remind also that, at least in my view, what Gail talked about, what's typical, that really is the goal for statistics in general, so that when we do confidence intervals and hypothesis tests, we're really saying, hey, is what we saw typical or not? What does typical look like? So I like to catch things in those frames. The question I'm going to be thinking about is, are boys taller than girls? And the answer obviously is yes, or no, or some are and some aren't. So to put it more in a statistical framework, we're really thinking about typical heights for boys and girls, which is taller. The data I will be using, I collected 2,000 values using the random sampler, which is part of the census at school in the United States. that the American Statistical Association has up on its website. This is free data. Your school can join it and add to the data sets. So encourage you to take a peek at that and think about ways that you can use that in your class. Just to describe a little bit about the data collection process that I used, I downloaded the CSV file, copied it into an Excel, and then copied that into the Nspire software. Gail was using the Nspire software with a pre-built sort of an applet type program. I'm going to be doing it more the way I would do it in a class, and that is importing the data raw and then manipulating it with just the basic menus and commands in the Nspire itself. So I'm not really using any programming per se, nothing pre-built as far as applets and those kind of things. Everything that I will be doing tonight are things that you could do with your class very easily. So the slide right now shows kind of what I think of as if I were going all the way to teach formal inference with the question of the heights that we posed earlier. The first three items are really where we'll focus our attention tonight. We'll allude a little bit to some of those later things. To compare two populations directly is something that's asked of in the 6th grade standards. We will look at how samples relate to populations and then use that to figure out what we can say about populations when we look at sample information instead of population information, which is the heart of what inference is all about. We'll be using the ideas that Gail talked about in terms of noting centers and measuring variability as our way of thinking about whether we're seeing differences in the populations or not. And when you move into the AP realm, then we'll try to quantify the way you're measuring center. So you'll be looking at sampling distributions of means. You quantify how much spread there is within that. You decide how much wiggle room you're willing to tolerate, and then you turn that back in terms of sampling distributions. So you would end up with a t-test. We're not going to do anything that resembles a t-test tonight. But the logic that we're going to be building is exactly what underlies that t-test. So let me get out of this guy, and let's look real briefly at what the raw data looks like. This is what it looked like when it came in from the sampler, and I pasted it into Excel. And you can see there's an awful lot of stuff here. I just kept the columns that included height. I deleted the handedness and things like that. But if you look here, there's data on lots of things, foot length, arm span, how long it took you to get to school, reaction times, all kinds of things. So there's a wealth of information in this project, and something that, as I say, is readily accessible, it's free, and you can even add your students' data to it. These are data, the raw data, as I brought them into the Nspire. And I'll take just a quick look at this and kind of see what we see. First of all, there's some values that you'll see sitting here. I made a column called cleaned. I don't think anybody is actually 13,621 centimeters tall. That's pretty tall. So there's some, let's call it erroneous data, either misunderstanding the question or just being silly to see if anybody would notice. So I've done a little bit of preliminary manipulation of the data, but not terribly much. And I wanted to show you kind of the result. This is the data here in graphical form using the kind of graph that Gail was showing a minute ago. This is for 4th graders. take a second and think of some things that you would say if you were describing these data. What jumps out at you? What do you see? Gail, can you see the chat window? I can't anymore.
Yes, I can, Landy. I'll report.
Okay.
Why are there heights near 0?
Great question.
0 centimeters. One big hump.
Okay, keep thinking about this. I'm going to move down and show you the same information for 8th graders.
People are worried about the gap, Landy.
Oh, they should be. And here's for seniors. So, do you see any similarities among these 3 different distributions? Again, seniors, 8th graders, and 4th graders. Think about similarities and differences.
So, Landy,
yes,
some folks are talking about this as skewed.
Okay.
Would you think that is skewed?
Okay, if I were describing this, I really see it as multimodal. So let me go back to the 4th graders where we started out. I see 3 distinct clumps. There's a clump in the sort of 0 to 20-ish range. There's a clump in the 40 to 70 range, and there's a clump that runs from 100 to 200 roughly. I would not call this a skewed distribution. If I were describing it to my students, I would think of it as multimodal. The main cluster is mostly symmetric. It might be a little skewed to the right. The biggest peak, as you see, the main clump is around the 140, and it tails a little further out to the right than it does to the left within that cluster. The others, I'm not sure I would ascribe a shape to them at all. But what struck me, and I guess let me back up and answer that question a little bit more fully too. I think of skew as being a property of the overall distribution rather than something of outliers. And multimodal distributions are harder to describe. In a sense, you've got more than one distribution playing at one time. So I really think of this as 3 different things that need description when I'm looking at it. And one of the things that surprised me when I looked at these data for the first time was not so much that there were misunderstandings or errors or something like that in the data, but that those showed up in essentially the same way at every grade level. I was not prepared to see seniors doing exactly the same thing 4th graders were when they recorded their data. My guess, and it's only a guess, is that the numbers in the 40 to 70 range probably are students who misunderstood and put inches instead of centimeters. Those are reasonable heights for people in inches. The zeros, there's no explanation for, other than somebody's being silly. These other numbers, perhaps a decimal slip. So those are meters instead of centimeters. I don't know. But what amazed me initially was that all 3 groups did basically the same thing. So that leads me to a lesson, if you will, that I would suggest, and that is that regardless of grade level, whether you're talking with seniors in AP or whether you're looking at 4th graders or people in between, we as teachers need to spend some time on the data production and collection process, and that means not just like in AP you focus on sampling and experimental design, but how do you use a ruler? What units are we measuring in? Before we actually carry out our survey or our study, do a practice run. Provide good instructions for the people that are going to be collecting the data for you. Doing a dry run probably is the single best thing you can do. And as I say, this is something not just for fourth graders. This is advice I would give to people that are dealing with real data collection at every grade level. By the way, this is a great place, I think, math teachers need to talk much more to colleagues in other disciplines. Our science colleagues collect a lot of data. They don't always share it across the discipline, but I found that by going and asking and saying, hey, look, you're doing interesting labs. Can I either watch your data collection or will you share it with me when you get done? Provides some great conversations back and forth, and it gives you a chance to influence maybe the way they do things. You might even get them to do a dot plot or a box plot sometimes, who knows. The second thing is, in terms of lessons here, is look for silly values and get rid of them, but with comments. So we know that the values down here in the 0 to 70 range are not real heights for centimeters. We can come up with an explanation for them, but I'm just going to ignore them for the remainder of what we do. So what we'll do for the next few minutes is to look at the original question that I posed, that is boys and girls separated. These are boys and girls together in these distributions here. We'll put them separated. And I'm going to also do one other thing that's a little bit different. Remember when we put the data in here, we have a single column of heights that we're working with. And that's a univariate data set. If I then plotted that using the Nspire data and statistics page, I can get it to separate by gender using this particular structure. The 84, you would think of a column of heights for males and another column of heights for females. That's actually the way I'm going to store the data for what we do next. So we're turning our attention now to the real question of boys versus girls. This again is fourth graders. The lower group is the orangish color is the males, the blue colors are the females. And
so
again,
Randy,
yeah.
Can you just revisit one more time? These are now some 1,000 perhaps random samples from thousands of data, right? What are these data?
I do not know how big the data. This is the same data. It's exactly the same thing we saw a minute ago. I pulled 2,000 values out of the database. I don't know how big the database is. But for our purposes tonight, I don't want to even think of these as samples. I want to think of this as the population. So what we're looking at right now is the population of all the boys under consideration, the population of all the girls under consideration. There are no other people in the world as far as we're concerned with this,
okay.
What follows from here. So these are going to be treated as populations, not as samples. We okay?
Yep, thank you.
Okay. So again, going through the ideas that you talked about earlier of what's visible in making the comparisons, I want to think about center and spread. And so this is the fourth grade. Like everybody, just sort of think to yourself, do I think that boys in general, the typical boy is taller than typical girl? And then we'll jump to seniors and ask the same question. These are seniors. Again, same color combinations. The orangish ones are the males, the bluish ones are the females. So take a second and let Gail know what your thoughts are. Typical boys versus typical girls for seniors and for fourth graders.
Folks are observing that for the fourth grade, there's no difference. The senior boys are taller. Fourth grade seems to be similar to boys and girls to each other.
Cool. Which is exactly what I hope you'd see. I also included 8th graders. I'm not going to show you those, but my surprise there was that I was expecting girls to be taller than boys in the 8th grade. They weren't. One nice feature of the Nspire is I can change the graph type real easily. I'm going to change these plots to box plots because, as Gail mentioned earlier, being able to visualize center and spread, some measures, is useful. So this shows me the median 140, median 141. That's darn close. And then I can visualize the interquartile range, which is the measure that is most easily visualized using built-in graphics. So I'm using the median and interquartile range as my visualization tools here. And as you see, looking at the boys and the girls, even where the outliers are is about the same. But these are about as alike as you could expect to see anything, especially just pulled out of the air. If we go down and do the same kind of thing with the seniors, oops, sorry, wrong place, and change that to a box plot, then it's really clear that while there is still some overlap, the central portion, that sort of the typical boys, clearly stand out as being taller than the typical girls within these two sets. Okay, so that's in a sense the comparison of boys and girls with no inference. But if we want to think about inference, then that means, okay, I need a sample, look at the sample, and decide what the population looks like based on what the sample did. And what I think is the important step in being able to carry that out is that we have to figure out, if I have a population and look at samples from it, I have to be able to figure out something about how samples from a population are related to the population itself. So I just want to show a couple of quick examples, and this is sort of the idea of simulation here, of actually playing it out. So what's on the screen right now, the blue large plot at the top is, again, 4th grade girls' heights. The group at the bottom is a subset of 50 females selected randomly from this population. So the lower part of the screen here is a sample of size 50 from the population above it. And again, the question is, what do we think about the relationship between the sample and the population? Now, the nice thing about Nspire is that when you see if I can get to take random samples, I can do as a command or Control R, depending on which device you're on, and with a touch of a button, I get another sample. So this is a different sample, same population, different sample, and I can look at a bunch of different samples from the same population and get some sense about how things behave. And again, if you want to think in terms of center and spread, visualizing those, then again, top one's population, bottom one's sample. Now we're not distracted by the fact that the number of data is different in the two plots. So let me go get another sample and see how the plot responds. So this time the central section is a little wider than that for the population. But by and large, if you were going to summarize what you're seeing, what I hope you'd say is, well, the center of the sample is about where the center of the population is, and the spread of the sample is about the spread of the population. And you'd want students to look at a number of these things to get to convince themselves that those statements are really true. So the question then is, okay, you said the center is about where the center is. How much wiggle can I have? These look like they're exactly the same. We didn't have that a minute ago. So let's go see if we've got here. Looks like it's about the same again. That's good. 140 and a half. So we're getting a little less variability than I really expected to see, to be honest with you. So what that does is sets up the question of, if I take away the population area and all I get to see is the sample, now what can I say about the comparison of the populations? So what I have here is just that. This is a sample of 50 taken from the boys group. This is a sample of 50 taken from the girls group among the fourth graders. Now, there's a bit of a visual difference both in spread and center between the two groups. But remember, when we looked at the populations, we thought that they were essentially the same. So we lose some precision, I guess, some confidence, if you will, when we move from studying the population where we know everything to studying the sample where we know something, but we know that what we've got is only a partial representation of what's really going on that is within the population. So the whole inference question boils down to, if what you've got is partial information, what can you say about the population from which it came, and what level of confidence you have with that? That last part is really where the upper level courses, AP, or courses that use, say, simulation-based inference, bootstrapping and the like, would allow us to get some measures of what's going on in terms of how much can my centers wiggle within a particular population. But at the 6th, 7th grade level, simply sit down and doing a bunch of samples, the way we've done here. Go back, take a sample, look at a graph. Take a sample from the same population, look at another graph. See how samples can vary. Students can get some sense about how far apart those samples can be and still be from the same population. If we look down at the senior situation, this is for seniors, again, sample of girls, sample of boys, and within the samples, again, there's a separation so that the populations were different enough that even though we have some uncertainty associated with our sample data, we still can see between them in a sense, that we can still tell that there's a difference between boys and girls. Had the populations been a little more alike, so somewhat different but not wildly different, and the 8th graders, turned out to be a pretty good example of that, then you may have some uncertainty as to whether you believe that there really is a difference between populations or not, based on looking at the sample. And so that's really what the fundamental question is from the formal inference side of things is how much wiggle can I tolerate in my sample before I start saying, okay, I think there's something going on here. And that's what AP and the t-tests and all those kind of fancy things do. It's a way of formalizing that. And I think I'll mention one other thing that is a tool that the Nspire brings to the dance here. I'm not going to do it in the interest of time, but if you take the ideas that we've used here in the sampling process that I was illustrating, let me go back to where I had the sample set up. I think it's worth looking at how simple it is to build a sample. If you look at the command that's used here, the command is just ransamp, name of the population, how big a sample you want to take, and the one means I'm going to sample it with replacement instead of without replacement. Sorry, it means it's going to be without replacement instead of with replacement. So that's all that's involved in getting a random sample in Nspire. What can be done is then to define a variable that is the mean, for example, of that random sample, and then do what's called a capture of those means. So I can, as I'm hitting Command R or Control R to generate sample after sample after sample from a given population, I can at the same time be collecting the means of all of those samples. And so the notion of sampling distribution can be built right in front of the student's eyes, one dot at a time. They can actually collect various samples and see that sampling distribution grow in front of them. I think this is one really cool. To me, that's when the first time I saw that on Nspire, I said, okay, this is worth the price of admission right here, to be able to do a capture and build a sampling distribution. But anyway, that's, I think, a good place to stop. As I said, to wrap up, what I think we've been talking about is that in order to understand inference, the real key thing is to understand how samples from a single population do and do not look like that population, and then to make it more formal at the upper levels, we quantify all that kind of stuff. I think I'll leave it right there.
Okay, so there's some questions here, Landy.
Okay.
So first, a couple of things. First, there's a question about the dots in the box plot, and what kind of algorithm was used to get those dots? Okay.
The Nspire uses the same rule that is sort of the convention within an AP course for, I won't say calling them an outlier, but at least making us think that we need to investigate them further. And that is, if you take the width of the box, that's called the interquartile range, the distance from Q3, in this case 148, down to 135. That distance becomes a yardstick. It's a unit of length. If we take 1.5 of those distances and append it to the upper and lower edges of the box, so if I take 1.5 of this distance and attach it here, anything beyond that point becomes an isolated dot. Same rule on the lower side, 1.5 of these, attach it here, anything below that point becomes an isolated dot. The lowest dot and the highest dot that aren't that far away become the ends of the whiskers.
Okay, thanks, Landy. So a couple of things. So, I mean, you heard Landy talk about distribution, but I've heard him talk about being really careful with your students, because he actually had you engage in 2 distributions. One of the population, he took that as the distribution of all the population values. And the second one was the distribution of the sample.
And those are what's visible here.
Right, and those are, it's really hard because as students keep doing this work, one of the things they keep messing up is what is the distribution of. And then he did mention the distribution of a sample mean, which is yet a third distribution. We didn't see one that looked like that, but he mentioned it. But it's important to keep these things separate for the kids.
And Gail, I'd go a step further and say that even use the word mean or standard deviation or interquartile range, there should always be an of what, and that of what should be of what kinds of objects and of what set of those objects. So here we're looking at perhaps the median of the heights of female students in the population, or the median of heights of female students in a sample.
And then, thanks, Landy, and that was kind of the point I think is really important to make. Again, someone asked where the data come from. They came from the Census at Schools, which is an international project that collects, it is voluntary data, but it could be kind of, you don't really know. The teachers in a certain school could say, okay, all the kids in my class have to submit this in, so it might be involuntary in a way. But the data are from both, you can get them region, you can get them country, so it's this rich set of data that you can have access to just by going to the American Statistical Association. And I have one more thing to say before I turn it over to Mike. I just want to point out again that Landy talked about how you can make Nspire do these things, but there are those building concepts statistics activities, and there are also a lot of statistics-inspired activities that are kind of applet-like that can be used to help you make sense of statistical ideas with your students. So over to Mike.
Thanks so much, guys. I think I do want to piggyback on Gail's last comment about the building concepts, because we kind of only looked at a very, very, very small example of some of the things that you can find on our website And so let me go there, education.ti.com. And under that Activities tab on the left, you'll find Building Concepts in Mathematics. If you slide down a little bit, there's Statistics and Probability. And so I'm just going to sort of peruse through a few of these. You can take a look at what's available. It looks like it starts in some grades 6 and 7 and continues up into grades 7 and 8. So whenever you have some time, please feel free to visit our website and look through some of those. We hope you enjoyed the activities that you saw tonight. There's, again, many more that will support statistics and probability in your classroom. When you leave the webinar, a brief survey will automatically appear in your browser. Your feedback guides us as we plan future online events, and we really hope you share your thoughts in the post-webinar survey. We're really excited that this year's T-Cubed International Conference is coming to Chicago in early March. It's coming up pretty quickly here. We hope that you'll be able to join us. I've mentioned in the past few weeks here just some of my personal thoughts on what makes the conference special to me. And I'll just, again, reiterate that it's the best professional development that I've ever attended, especially because I get to talk and meet people like Gail and Landy, which are just really neat people to have kind of in your back pocket and people you can email with questions or comments. So please feel free to visit our website to learn more information about the T-Cubed International Conference. And as Gail mentioned earlier, we are doing a webinar giveaway, and tonight's lucky winner of the webinar giveaway for a T-Cubed International Conference registration is Angela Francis. So Angela, congratulations. We hope to see you there as well as everyone else. Please feel free to continue the conversation. There were some really great questions that were being asked in the chat and the Q&A windows tonight, and lots of good responses and thoughts. So please keep that conversation going on any of the major social media outlets. To receive a certificate of attendance, please click the link in the chat window. Also listed is a link for the documents that were used tonight by Landy and Gail, as well as the PowerPoints. Everything's all there. If you happen to miss this for any reason or it's not working, have no fear, you'll automatically get a follow-up email in a couple days. In that follow-up email will be a link to the recording, a link to the certificate, as well as a link to the documents. And if you happen to be watching this on demand, go ahead and copy down that certificate link into your favorite browser to get your certificate. If you're in need of any post-webinar follow-up, feel free to give us a call at 1-800-TI-CARES or send us an email at ti-cares@ti.com. Thanks so much, Landy and Gail, for everything you shared tonight. I saw a lot of positive comments again in the chat window, and I just really appreciate everything that you guys put together for tonight. So thanks so much.
You are welcome.
Again, we're really excited to see everyone on tonight and hope to see you back online soon. Thanks again, everyone. Have a great night.
Thanks, everybody.